Good afternoon, everyone, and welcome to this first seminar of the AI Research Unit. Sorry for the delay. We had some problems, especially for those of you who are at home. So it's a great pleasure to start this seminar series with an old friend of mine, Joachim Buhmann, who's a professor of computer science at ETH in Zurich. And he's a world expert in the field of machine learning. We know each other since, I think, more than 25 years. Actually, the first time when we met was in Venice, very close by at Bottacin, when I was running the first EMM CPR workshop. And then we've been in constant touch. We've been working together on a very nice project for a few years. And so it's a great pleasure that he accepted my invitation to come and to give a talk today. He will be talking about very provocative topic, as is always the case with Joachim. And so the title of the talk is Machine Learning and AI, Paradigm Shift in Human Thought. And thank you again for joining us.
Thank you very much. Particular pleasure to be here. It makes me feel younger than I'm actually. If you are approaching retirement, then you cherish the memories. So machine learning is on the mind of everybody, and in the popular press, it's usually referred to as artificial intelligence. But I want to get more concrete, and that's why the title could also be. Okay, I'm not sure why it's no longer working now. Oh, okay. The title could also be Algorithm Validation for Data Science, but it has the same quest from an epistemological point of view, from a philosophical angle. And so I would like to talk about validating algorithms in data science, and that is the engine for machine learning. So the world in which we live is a world of data, and here at the macroscopic scale, you have all seen this. It's a Nobel Prize winning piece of work condensed in this picture. This is what is closer to what where I am involved in medical information. And we need computers. In the beginning, it was the one where von Neumann actually was standing close by, and today for the Swiss High Performance Computer Center, you have these types of machines. But the purpose of all this is to generate value. And in order to generate value out of data, you need algorithms. So these algorithms then deliver the values. And so what I would like to talk about is how we can find scientific guarantees for designing algorithms so that the interface to values is well defined. So values in this world come from many different angles, but in some sense they are, quote unquote, from a scientific point of view, arbitrary. Now, I don't want to go in these discussions, especially you might have seen the Ukrainian flag on the first page. So values is a difficult thing, but if you design algorithms in the context of artificial intelligence, it's particularly important that the interface between the world of values and the world of computing is sort of well established. That's something I like to do. Now, data, another Nobel Prize winning image of the black hole in the center of the Milky Way. None of the colors here are actually true. They are interpretations. So data are already interpretations. And in my field of medical informatics, these are the type of data. So what you see is, you see gene expression data, you see metabolomics data, or proteomics data here for finding out which peptides are in a certain substance. You have these images of cell slices and so on, and I will come back to this picture here later. You might also have data coming from a human expert, because we need the human interpretation of our data in many different contexts. So these are my cardiology reports, or you have data coming from sort of quantified self. And you have these devices everywhere today. So data, we are flooded with data, and the problem is we have to make sense out of this data. So data collection is not a new thing. In prehistoric times, humans carved on bones and noted something down there. Famous in antiquity was the Library of Alexandria, or in the Enlightening period when people collected death statistics to make predictions for society. So there's a very long tradition, and in particular in the Enlightening period, people understood that from a philosophical point of view, observing the world and making models is something which has tremendous impact. And in particular in physics, you have seen these successes. So what has changed with digitalization? Why is the analog world different from the digital world? My answer is not only because I'm paid as a computer scientist, my answer is it's control, and it's controlled by algorithms. So algorithms allow you to do efficient data management, discover models, test hypotheses, and find solutions. And you might actually summarize at least the last three, but also the first one as intelligent thinking, or at least kind of intelligent. Now, when it comes to intelligence, you have to define what you mean by that. My definition is intelligence is when an algorithm is able to do counterfactual reasoning. So the algorithm can evolve the current status into the future, ask if you like the future. If you say no, you have to act today, and then you test out in a counterfactual way how you should act today so that the future is according to your life. It's very clear that's what a doctor is doing. A doctor wants to have an impact on the patient, and so any prescription for a therapy should be triggered by the outcome. So it's counterfactual outcome planning under the uncertainty of what. So let me come to algorithms. Algorithms for me are relations between data and decisions. And you know, Marcello is one of the causes why my worldview on how you should build models in this world. I was trained as a physicist, and I thought if you don't have a cost function, you don't know what you are doing. He is the cause why I abandoned this belief, and it was very painful, I must tell you. But I think it's now more general than it was ever was. So for me, that's the relationship between data and decisions. So pattern discovery, pattern interpretation is difficult. It's extremely difficult. And so I don't know how many have seen this picture. It's something along the lines of a Dalmatian dog. So if you don't, who sees what it is? Okay, let me give you a hint. Who can now see it? What? No, I gave you a hint. Okay, now you get the hint for a longer time. So usually what I'm saying is you don't see it now, you should consult your neurologist of choice. So it's difficult to do this grouping. Already in the Enlightening period, people were thinking about these issues here. It's referred to Leonardo da Vinci, these problems of interpretation of image information. It's combinatorial optimization, grouping as in the first part, but also a high-level semantic interpretation. And how difficult it can be is this with the next partially correct image So if you feel offended, then you have made a wrong figure ground segmentation process. So there is no woman in that picture. But the brain cannot tolerate that accidental arrangements give you semantic meaning. That's why you imprint the semantic meaning. So it's a difficult business, and you want to understand this more in detail. So a project which is also related to our SIMBAD project was started by Thomas Fuchs. He was looking at these types of data here. So you see histological slices with different types of stainings, but also metabolomics, gene expression data, and so on. And Thomas was then asking the doctors what to do. He wrote them an app to do the annotation. One of the doctors was so diligent to actually got an eye infection over the annotation. So he got the data and the information, and then you want to put it together to some knowledge. And the knowledge might be an explicit theory which you develop, or it might be an implicit embedding on a functional relationship in a deep neural network. And in the end, you want to generate a value. And this is not the smile on the face of the patient anymore. This is this type of survival data. So in these probably 10 kilobit, what you need to code, whether you are green as a patient or red, that is all the information which is essential. This bit, everybody cares. The doctor, the patient, and society. And to be very concrete, if you have clear cell renal cell carcinoma, this kidney cancer, which was studied in this project, and you are classified as green and you are red, your last half of your life is miserable because you are exposed to chemotherapy and equally the other way around. So this is an essential bit which you want to extract. You go from hundreds of gigabytes of information down to these 10 kilobytes. Where in that pipeline have we actually extracted the bits about green and red? That is the challenge, I would say, of these types of data processing pipelines. And you have to immunize your pipeline against misinterpretation of the noise in the data. So what is the problem when you extract a value from data? One problem goes back to Kolmogorov, and he taught us that if your input to an algorithm is random, then the output is random, because the algorithm, even a deterministic algorithm, implements a functional relationship. So what does that mean for a data science algorithm to actually be correct? We assume in computer science that correctness, establishing correctness of your algorithm might be very complicated, but at least you have a concept of correctness. Like in sorting, we know what a total order is, so we can actually check whether the answer is correct. What is the correctness for data science when the output is a random variable? It's not clear. So Shannon told us that the outputs should be typical. They should be typical solutions. And I think that relates this part of science to statistical physics, probably the most successful theory ever built. The fluctuations are essential for understanding when a solution is correct. So it's this trade-off between your goal and the arbitrariness from the fluctuations, which are then summarized in the entropy and posed together. So Wapnick, for our field, told us that algorithms have to generalize over noise and model mismatch. And we should understand what it means that algorithms are robust. And you have to regularize them in case that they have too many degrees of freedom and start interpreting. And ultimately, in the future, we have to solve the problem how algorithms can autonomously improve their performance. And in particular, I would like to point out that it's a non-trivial challenge to define what performance is. So for me, this is sort of the effective way of how to characterize an algorithm. So you condition on your input, that's the data you get in our application field from the patient, and you want to predict the information which you want to get out of this analysis. And you might even start taking into account interventions so that you have a full-fledged planning process in order to do outcome control. So the philosophy is data science algorithms map uncertain data to uncertain hypotheses. So therefore, the data science algorithms are abstracted by posterior probability distribution. So effectively, the effect of an algorithm, if you summarize it, the effect of an algorithm is this posterior probability distribution, which is implemented by the algorithm. So the challenge now is, what is the appropriate score to estimate? I wrote the optimal posterior, PA, A refers to algorithm. But maybe it's better to say to estimate an optimized or an improved whatever posterior. So you need a criterion to tell you that some posteriors are not as good as others. And that criterion is not clear. So let me remind you algorithms, the idiom of modern times. That's a very nice paper by Bernard Chassel, who basically made the argument that for 5,000 years in science, if you go back to the 2,000, 3,000 years to the ancient Greeks, the model was in the driver's seat and algorithms were in the back seat. Today, it has changed. The algorithm is now in the driver's seat and the model is in the back seat. The model is commodity. In many applications, the model is a linear model with millions of degrees of freedom, and the choice of these degrees of freedom is the essence. So it's an algorithmic challenge and no longer such a model challenge. So this is the algorithm for doctors to follow when you have a heart attack. And you see there is a color coding of the terminal nodes, transport of death. Now, I don't want to go into the details. What I want to stress is that algorithms have been actually analyzed according to runtime, memory usage, energy consumption, and maybe some other sort of performance factors of algorithms. To a much, much smaller degree, they actually have been analyzed with respect to robustness and generalization. So that's why I put here X's for not yet established. That is the challenge for the future. And I will come back at the end of this lecture why I think this is the big challenge which we have to master. So for me, learning algorithms explore reality, and it's a very complex stochastic reality. Now, this is a model assumption. I'm not claiming that I know for sure that the world is stochastic, because that means the world actually follows Kolmogorov's axioms. But that's the best way of making progress in model building with our current observational tools. If we use less assumptions, it's much less clear what we should. And by the way, this is a more current update of this decision algorithm for Harvard. So in a nutshell, you get these data, here the gene expression data. Okay, so you see the gene expression data, you pump it into an algorithm, and then comes out a posterior probability distribution, and you want to understand this posterior probability distribution. So my argument essentially is the following. Humans are no longer inventing models as they have done up to today. Humans are now controlling algorithms, validating algorithms, because the models are actually generated by algorithms. Machine learning is an algorithmic approach to on-the-fly producing models. So validation of algorithms, I would like to separate essentially 3 different levels. The first one is humans know how to solve a task. Let's say sorting, we know what a total order is. So then you find a lot of information in the libraries on how to do that. That's algorithms design and engineering. Very well studied and many experts in the science. The second level is humans can solve a task, but they don't know exactly how. And sometimes they actually have no clue how they solve it, but they still solve it. And so this is the area, this is the field of supervised learning. The ability of a doctor to rationalize about their own thinking process is much less developed than their experience. So when I go to the doctor, I no longer ask, why are you doing what you are doing? Because first of all, if the guy doesn't know, they usually don't tell me. And second, I don't want their experience to be contaminated with my quest for them to rationalize what they are doing. And I know that is not as good as their experience. So that's why we use human experts as input-output relationship sources so that we can mimic them. Now, the real challenge is the third one. Humans can't solve it either at all or not good enough. So the first one was AlphaGo 0, which basically shattered in particular in the Asian world, in Korea, the belief of humans to be superior to machines. And that is kind of, when you use autonomous learning by self-play, it's kind of category 2, but not exactly. In autonomous learning by self-play, the computer emulates, according to very simple rules, the game, which provides you then with the feedback of the teacher to actually improve by yourself. So the game is so simple that the computer can emulate the teacher. And it's kind of sort of supervised learning. You might add. And I like to add. Now, the real problematic area is unsupervised learning. And in unsupervised learning, you want to get predictive information out of your data. And what are the criteria for that? So I would like to stress that since the enlightening period, with a scientific method, we were always asking for reproducibility. But if you have a very simplistic worldview, it's very reproducible because there's no information or there's hardly any information. So there's a trade-off between making the most out of your data towards your values and at the same time to be reproducible. And this trade-off generates the structure upon which you can then design it. So that's the necessary trade-off. Now let me. I have now, I think, 8 slides with a little bit of simple texture on it, just to set the stage. The traditional design of posteriors comes from physics for very good reasons, because it's the maximally robust type of posterior distributions. You define a cost function which maps the hypothesis class times the data into the reals. You call it a cost function, Hamiltonian energy function, you name it, or a risk function for statisticians, and that's why I use the simple R. And usually what you have is you have a number of different cost functions, and you want to select the cost function which is most suited. So the Gibbs distribution is given here. Everybody knows that calculating the denominator is the problem, but I think the even harder problem is to find what is the correct R. And this was the creative act of humans so far in that game. And F is the free energy, summarizes. So that is one possible way of starting in that game. So what is essential in machine learning is that these posteriors generalize. On the previous transparency, you have seen this beta, which is sort of the concentration control parameter for the Gibbs distribution, whether it's very peaky or very broad. And the physicists usually couple their systems to a heat bath, so the parameter beta is directly representing the heat bath. So they don't worry about where beta comes from. Now, as computer scientists, there is no heat for our algorithms. So the algorithms see only uncertainty in the input. So you have to convert the input via the algorithm in an uncertainty for the output. So implicitly, an algorithm has to have a way of representing these control of the posterior. So let's assume that I have two data sets drawn from the same experiment, original experiment and then control. And he gives me the data set X prime and X double prime. And X prime and X double prime might be really complicated data structures, let's say images or very large graphs or whatever you have in your particular application, referring to the data sets which we were discussing. Now, an approach to put some rationale in that whole game is, you say the expected score might be the description length of the hypothesis conditioned on your observation. So that's, I would like to start with that because it's very generally accepted that compact descriptions of hypotheses might lead to good models. And that means you take the expectation over all hypothesis theta, given your training data X prime, and you evaluate your score function for that particular hypothesis theta on your test data X double prime, or on your validation data X double prime. And then the score is minus the log of the posterior. So this is kind of out of sample description links. And if you now plug in the Gibbs distribution from the previous transparencies, what you see is, you see that you have the generalization error scaled with beta and sort of a normalization minus the free energy. So the description length is very closely related to the generalization error. And I will argue later that this is not the right thing. Just that you stay tuned. This is a provocation. So what can we do? So the conceptual framework I'm suggesting for algorithms validation is, I need a set of experiments. So they are enumerated with E here out of a set of possible experiments, and they generate the data XE. And then you have a hypothesis class theta out of capital theta. And the goal is to learn a hypothesis. I took the plural here on purpose because for most interesting problems, you don't have a unique answer in terms of a hypothesis. And that these hypotheses depend on the data XMC. So the strategy is you use an algorithm A, and that A maps the data space times the experiments into the hypothesis class. And so you get a theta which depends on your data from experiment. And I come back to that experimental notion on the next couple of slides, but I think it's quite important. So then you have the pipeline here in terms of something which is close to what you are doing in network science. You have your gene expression data, you convert them into a correlation matrix. There are various ways of how to do that. Then you abstract these correlation matrix into a graph where you only keep the high correlations. And then you want to find, for these particular analysis of gene expression data, you want to find genes which sort of behave in a similar way. And that is a graph color. And I put here several results in the solution set, indicating that you cannot expect that one solution will be the best one. But the question is, the real question is, what is the algorithm? Because usually you have dozens of algorithms on the market. And when we first got together, he had a dynamic system producing answers. I thought this is bogus because you don't know how good that is. And I had my cost functions where I could hardly calculate Gibbs distributions, so we were crudely approximating them. So in some sense, we all had our ways of approaching these algorithms design. Correctness of machine learning algorithms. Some of you might know that. The output of a machine learning algorithm, as I argued according to Kolmogorov, are random variables. Let's do the following experiment just to sharpen your intuition. You have a biased coin, 60% head, 40% tail. Now we make an experiment, we repeat the coin flip 1,000 times. And I ask you now, what do you want to sell to your customer as the result? Make a prediction for the result. Okay, so which sequence do you want to report? What students usually learn is you follow either the maximum likelihood principle or the maximum posterior principle. And the maximum likelihood sequence is only heads. So I get back to the question, what is the correct answer? According to a generally accepted score, the maximum likelihood principle, the sequence which has the highest probability is atypical. You can't buy anything for that because it happens too rarely. This is, you know, the problem goes away when you condition on the data and you never think where the data are coming from. But that is not what our customers want us to think about. They want us to take everything into account. That's why our guarantees have to take this into account. That's why Paris's Nobel Prize is so important, because that applies to everything what we are doing. It's the randomness in the input and the randomness of your algorithm which produces the joint randomness in the output. And that's what we have to understand in all sciences, not only in statistics or disordered systems. Okay, so I would claim we often return the wrong answer, in particular when we have a random instance of an integer linear program. In some sense, my coin flip experiment is exactly a linear, integer linear program. Okay, so MDL for posteriors, there's a catch with that. The problem now which we face is the algorithm abstracted by a posterior can modify itself. So the algorithm in principle could start ignoring part of the hypothesis class. And I forgot to make clear. For my current analysis, I assume that the hypothesis class is given. Is that a dramatic assumption? Yes, it's a dramatic assumption, but we all make this assumption when we write an algorithm, because if you cannot write an algorithm when you don't know what a legal answer is. Whether it's the correct one or not is unclear, but at least you must know what type of answers your algorithm is supposed to. So in some sense, this is also what you assume when you use a machine to solve the problem. So given So I would like now to argue that you have to tame the learning algorithm in a certain way that it cannot start ignoring large parts of the hypothesis class. And for this, I need this experiment. So what we now do is the objective which I like to start out with is the description length of the posterior, as I pointed out, given test data. So it's minus the log of this enumerator posterior distribution, and I normalize it with that term basically integrated over all possible data sets. So P epsilon A theta is the expectation over the data of the posterior. Now, if you take this part here and you actually look what it is, it's the expected Kullback-Leibler divergence between the two posteriors minus the mutual information between the data and your hypothesis. So for selecting an algorithm, I do not want to count the bits, which I need in any case to establish the relationship between my hypothesis and the data. Because I only want to use the bits which make a difference between my first and my second experiment. This is the generalization test. A hypothesis class which is complicated relative to a hypothesis class which is simple is a design decision. And it has nothing to do actually with generalization. Generalization is the effect that you repeat your experiment and then you get a different answer. So this term is lower bounded by Jensen's inequality when you pull in this expectation here over the hypothesis given my training data into that log. And so essentially the outcome of our project was for my group or for me personally was the insight that information theory allows you to make progress on this question, how you can quantify the information an algorithm is extracting relative to a hypothesis class. So essentially, an algorithm is better when, given the fluctuations in the input, this algorithm can make more precise, more concentrated answers in the hypothesis class than a competing algorithm. If you know what should come out, you are solving the wrong problem, because this is unsupervised learning. There is no expert who gives you information about the correct answer. So the trade-off between a precise answer, which is repeatable, that trade-off is exactly what we want to explore. Now, what is this catch of the algorithm of trivializing the answer? So let me point out here. It's very clear. If you look at this object here, an algorithm which basically commits to only one hypothesis in the end and concentrates all the probability mass on that one hypothesis, that algorithm has a 1 here, and minus the log is 0. So this algorithm has the lowest score value. And obviously that is not the answer we would like to have. So we have to prevent an algorithm from actually ignoring the task. And the task is to make a selection in the hypothesis. So what you would like to require, and that's why I need this universe of experiments, what you would like to require is that for all hypotheses out of your hypothesis class, there exists an experiment and some data from that experiment, such that if the algorithm is processing these data from that experiment epsilon, it gives you the answer theta. So that basically means you go through your universe of experiments and every hypothesis is necessary. Now, what are these experiments in the context of the example I have shown you so far, namely these graph partition problem? An experiment for me is the arbitrary design decision of the modeler, or in that case, the algorithm, to enumerate the vertices. Any permutation of the vertex index is a legal new experiment. And obviously, that has nothing to do with the measurement process, but any measurement process you have in mind will be transformed by such a choice. And so you want to take this into account. The algorithm should not pretend that there is a preferred enumeration of the vertices or any other kind of equivariant transition you might, transformation you might have in your problem. So since I'm here in Italy, you know, Galilei invariance is one of the very powerful tools to get the invariant quantities in mechanics and so on. So these are precursors of this type of idea. In order to now make this operational for our probabilistic inference, I define this probabilistic richness. And I basically say, if I take the expectation of all experiments of this prior probability for the hypothesis when I integrate over all possible realizations of my data, if I take this expectation over all experiments, then this prior P of theta should be as close as possible to the uniform distribution, which basically means I need all my hypotheses in my hypothesis class. Now, that might not be achievable because no, the maximum entropy principle tells you that when you shake your cost function a little bit, that one distribution is particularly little changing, and that's the Gibbs distribution. So here I'm saying there is no part of my hypothesis class which I can actually ignore, because that would mean I have to rule out a set of experiments which are not under my control. Yes, if you don't know, basically what you are saying, if you don't know which experiment has been conducted, you should expect that every hypothesis is the same. Now I told you that we have to be very careful with the interface between value and our algorithmic design. So if you know a priori, according to your belief system, your value system, that certain hypotheses are not preferable, but you don't want to rule them out, then give them a low priority here. And that would mean you are abandoning these quests that this posterior here is close to the uniform distribution, but is close to the ethically preferred hypothesis which you have designed a priori. But that is a piece of information which comes from the human user. It has nothing to do with the algorithmic selection process. It's just an input to the algorithm. And that's what I mean. Keeping the influence factors very well separated is a quest of our times, because that's the only way to make these value debates sort of rational, because part of the value debate is a scientific question and the other part is by choice, or I would say arbitrary, and that's why you want to keep these two influence factors separate, and you want to define exactly what the interface is. Here is one of these interfaces. Yeah. Yes, if I require the uniform distribution, then I am preventing my algorithm from arbitrarily ignoring hypotheses. If I'm not, since the algorithm can modify itself autonomously, I have to constrain this in order to have a well-defined mathematical problem. So And there are applications where the data force does not allow the uniform distribution. And then this minimum of the Kullback-Leibler divergence will have, with that entropy here, will have then a finite value, and there's nothing what you can do about it because it's a property of your data source. But still, if you talk about combinatorial optimization, the arbitrary enumeration of the degrees of freedom of your combinatorial object, that is still not fixed in an arbitrary way. You allow any kind of starting point for formulating your setup, and the algorithm then can modify itself, but has to adhere to these richness conditions. Okay, now it's simple. I have now two parts. I have the description length part and I have the richness part. And there's a trade-off. They are fighting each other. And I have a lower bound from Jensen's inequality. And so in case that this entropy over the hypotheses is actually maximally in the hypothesis class, and I'm talking about discrete hypothesis classes for the time being, not because I'm a computer scientist, but I want to avoid all these measurability issues that come from this hypothesis classes. And I know enough very good mathematicians. So that's basically what then comes as a lower bound, and we can prove that this is larger equals to 0. Okay, but this inequality made a very big change. It basically went from here, where we have the description length argument, which was basically a test error, as I argued, to a kernel which compares two posteriors. You have the posterior given the training data and the posterior given the test data, and they have to agree. So that's the stability quest. But at the same time, they also have to be very peaky, because otherwise they agree and are very broad, and due to normalization, the kernel will be very low. So this inequality here, where is my cursor? This inequality allows you to go from a concept which I call partial ordering concept with cost functions to a topological concept. And the topological concept is much more fundamental because it's the basis of information. So that's how it looks like for Gaussians. When the prior is well agreeing, but broad, normalization pushes down the maximum value here, and you get a low value. When it's very peaky, but it's not agreeing, you also get a low kernel value. And somewhere in between, there is an optimum, and that's the optimum. So in essence, this theory allows you to derive a temperature for a computational problem because it converts the fluctuations in the input in effective uncertainty in the output. So the algorithm is a temperature generating mechanism for the hypothesis, for the uncertainty. And I think that's what is essential in algorithmic processing. You have a hypothesis class. Usually these hypothesis classes are too rich because you want to have many choices available. You don't want to burn into your hypothesis class your prejudices. And then the inference principle should regularize itself autonomously. It's not the mathematician who has to suggest the regularizer, because they are chosen according to different concepts, let's say provability of some results or whatever. And quite often they hide it in the norm they are using. No, an algorithm has to have everything under control, so it must be a theory which is self-contained in order to give an answer to this algorithm. What do you do then? Now we have established that the expected log kernel here is lower bounded by, or has to be lower bounded by a sample average of these log kernels on capital L pairs of training and test data. But since this is an empirical estimate which we maximize. You have to subtract the penalty, otherwise you are too optimistic. So this is now a question from statistical learning theory. We want to maximize an expectation value where we don't know the probability distribution of the data pairs. So we emulate with an empirical estimate of that expectation value, and we subtract an overfitting penalty for the fact. Let's assume that we can actually evaluate this lower bound. And to be honest with you, what I know is we usually use L equals to 1, capital L equals to 1, because our biologists only get us one repetition of an experiment. And we don't know what the penalty is. But that is a separate question here, so I don't want to go into. This is statistical learning. What I did before is I wanted to derive a concept for actually getting you the kernel here and the logarithm of that kernel. And the logarithm of that kernel effectively is a mutual information. So then you have, you use this lower bound, you maximize the posterior by basically adapting your posterior. And that gives you an optimized posterior or an optimal posterior over that set. And then you can actually process new data, future data with that posterior, or you sample hypotheses from the intersection of the posterior and the training data and the posterior and the test data using the optimized beta values, which you have to write. So why should you believe in it? Well, there is at least one case, the very simple binary symmetric channel from information theory, where you minimize the Hamming distance for comparing bit strings. And in that case, you get exactly the correct channel capacity. So for this case, it's exact. And I also know that whenever theta, the hypothesis, is a sufficient statistic on X prime and X double prime, under these circumstances, the score which I derived, this kernel, is essentially the mutual information. So that is all. And if theta is not a sufficient statistic, like you have it quite often in statistical physics, then you get an approximate sufficiency. You get an approximation to that, and you get some deviations from optimal. But it works quite well also in these situations. So let me now come to experiments. You tell me. Time wise, I think I will. Yeah. So yeah, that's like. So we have experiments in different areas. An interesting one is neuroscience. Why is it interesting? Because in neuroscience you have, first of all, surgery in neuroscience is a delicate thing. You don't want to do that. So any type of diagnostic tools which are minimally invasive are very valuable. The problem is minimally invasive in the brain is you get zillions of interpretations of what people read out. So let's look at the following pipeline. Fiber tracking and cortex pulsation. You have these diffusion weighted images, 10 gigabyte per patient. So you might have hundreds of patients, so large cohorts. This is a lot of data. Then you convert these diffusion weighted images into diffusion tensor construction per voxel. And then you have a fiber tracking algorithm which follows these diffusion tensor, the elongations of the diffusion tensor in these different directions, and you claim that this is sort of a fiber in the brain for infection. Later on, you use the connectivity pattern from these fibers in such a connectivity matrix, and you start grouping your target boxes according to the seed boxes. And then you can start coloring the surface of the brain, for example, for either for diagnostic purposes or for surgery planning. So I had two students working on this. So Victor was essentially concentrating on the fiber tracking and the diffusion tensor construction, and Nico on the partitioning. Unfortunately, they did not work together. So okay, so you want to use it for surgical planning, as I indicated, when you have a tumor here, also for radiation therapy planning and so on. Or you want to use it for system neuroscience to treat, let's say, diseases like schizophrenia and so on. What do? Imagine that you have these voxels with all these diffusion tensors here, and then you have an incoming green direction, and then you want to predict the next direction given the data in such voxel and the neighboring voxels, and that would also allow you to generate with an algorithm which can do this type of tracking. You can generate artificial training samples for an algorithm. And the risk function is basically the scalar product between the incoming direction and the prediction of the out. No, it's the scalar product between the direction you want to predict and the function which maps the data and the incoming direction into such an algorithm. And you want to know the uncertainty of that function and the expectation. So you train a deep neural network in order to convert this input, X and input, into a predictor for the mean direction and for the uncertainty of that mean direction. And that's what you get. You concentrate here on a particular voxel. I don't know if you can see this. There is a green dot on the images. That's a voxel, and we consider now all the tracks, all the fibers which go through that voxel. At beta hat divided by a sort of a normalization constant of 0.1, you get a lot of uncertainty in your estimation. At a beta of 1.3, it's very regular. And somewhere in between, that's what you then see. If you use this kernel argument, the theory gives you the bold curve in orange, and the evaluations of the respective log kernel values which we derive are the crosses. So that net matches very nicely, and I would sell to my customers, this is the best value to store. So this is the optimal interpretation. Given the uncertainty in the input and the model with the algorithm. And then you can produce these types of images. So I'm not claiming that this is scientifically relevant, but I'm claiming that this is statistically relevant. And usually, if you have no statistical relevance, you have to keep a lot of fingers crossed that it becomes scientifically relevant. So this is sort of a sanity check for your algorithmic pipeline, that you actually can control it. Whether they then give you scientifically valuable results has to be determined based on the set. Okay, if you look here, for example, these are benchmark data which they use to compare different fiber tracking algorithms. In the benchmark data, you had a completely implausible. Nobody figured that out. Here, you just process this benchmark data and you can highlight it and you can take it out. So it also helps you to clean up data which are implausible. Humans can't do that with that. That's why they didn't do that. Now, the next step is systems neuroscience. You convert such a connectivity pattern into a graph. And let me skip this because I'm running out of time. And the pipeline then gives you pipeline then gives you, as an algorithm, a zooming, almost like with deterministic annealing through the resolution space. And here on the left part, you see the coloring with different shades indicating the uncertainty of the different areas. And now we go through the maximum, and the informativeness is now decaying because the algorithm is interpreting the noise in the uncertain boundary regions too crisply, and that is wrong. So here the algorithm is overconfident for these types of values, and that's exactly what you want to do. So these are the type of I think, diagnostic tools we need so that actually algorithms can autonomously suggest where are the weak points in the algorithmic pipeline. And let's be honest, the weak point might be the software to evaluate some of the intermediate results because there are bugs in the software. And even that can be interpreted as an additional uncertainty which has to be quantified. So let me skip this. We have another project where we want to infer from echocardiograms the shape of the heart, and in particular, what is going wrong in the dynamics of that. I don't want to go into details, but we also use deep neural networks, and in particular, automatic control of the regularization parameters so that it's fair. Okay, so I like to close with a couple of remarks. Also to contribute a little bit to the public discussion on artificial intelligence and machine learning. So there was an algorithm a couple of years ago that an article in the local newspaper NZZ, Zurich, algorithms are very dangerous. So I thought, like firefighters, I now get a raise because I'm dealing with very dangerous things. But that wasn't the case. So what is it? Well, here's a book on the death algorithm. Algorithms actually suggesting who gets a treatment, who gets not a treatment. So all this is problematic, and I don't want to trivialize it. But this is interesting. So this is what in 2016 Americans were dying of. And so you see, 30% of heart disease, a little bit less of cancer. You also see this, you can't probably read this down. This is terrorism. And then there is the hierarchy of all the other causes. Now, this is what they looked at Google. It wasn't very interesting that burgers are not good for your heart. So blue is now down to a few percent. Cancer is still very popular because, it's frightening. But terrorism gained in interest. And this is what the newspapers report. And I tell myself, if we are such lousy risk assessment people, then we need tools to bring more rationality in our decision. Because this, to a large degree, determines how public funds are also spent. So what is the take-home message? The take-home message is high complexity is not very good for human brains. And that's why we ignored it so far. But now the complexity is at our doorsteps, and we have tools to master. So we have to empower these algorithms to at least be rational and credible so that they make the best out of the data which we are feeding to these algorithms. And we have to have clear criteria what is good and what is not so good from a scientific. And we have a clear interface. We have to design clear interfaces to our values because they come from a different world. They are not necessarily scientifically addressable. But there is an interaction there, and this interaction has to be designed. So you might ask, what is missing? And what is missing is the scientific method for really, truly autonomous knowledge generation. You ask questions, that's now the Wikipedia version of the scientific method. You propose hypotheses, you conduct experiments, you analyze the results, you go through that loop until you are tired, then you postulate the theory and you go back to ask questions. So that's how Galileo first described it, and you see his writing in the back. What has changed today is at every arrow here, there is an algorithm. If we can't validate these algorithms, this is not working. And I would actually claim that the algorithms are the models, because the algorithms are the posteriors. That's essentially what the model is. And for quite some time in the future, we have to live with the coexistence of brains doing modeling and machines doing modeling. So we better pay attention to the interface between these two inference engines. But in the long run, the only way to make sense out of super complex situations with millions degrees of freedom and completely unclear quantitative descriptions is that we empower our algorithms, which are our devices to make concrete mathematics in the broader sense work, to empower these algorithms to self-correct, to find out when they are reading the tea leaves. So let me now summarize. Why is that a paradigm shift in human thought? And actually, I should put the exclamation mark after the talk here. So knowledge has been created or discovered, depending on your philosophical sort of tune, by human brains. And in the future, it will be done by self-learning machines. So we have to come to grips with that. That's a fundamental change, because we defined ourselves as self-aware thinking animals. So algorithms model posteriors of unprecedented complexity that will be never understood by humans due to our limited memory capacity. So what we can hope for is we can hope that these super complex posteriors are embedded in a multi-scale hierarchy where we start climbing in understanding a little bit up until we are flooded with degrees of freedom which we can't handle. So machine learning empowers algorithms to infer very complex theories. I would like to have a theory for my personal life, conditioned on my genome, maybe conditioned on my marital status, because I think it's stable, and generalizing over all the other kind of arbitrariness in your lives. We never accepted this question as a scientific question in terms of to build a scientific theory. And the reason was we couldn't do it. It's not that this is philosophically forbidden. Personalized education is exactly like this. Many degrees of freedom, we need tools for doing that. And we need these tools in a self-correcting way so that they autonomously adapt to the customer. And the predictive power of data-driven models has to be validated, I think. It's not a verification because there is no prescription against which you can check the action of your algorithm. It has to be validated that these are actually admissible models for our thinking about reality. And with that, I like to close and thank you for your attention.
Very inspiring talk. Questions? Oh. I have two questions that here related to that. So I got confused because up to a certain point, I thought that you were actually building a sort of thermostat, in which
fixed temperature. In my language, temperature is a microscopic variable. And then what you wanted to do, we know the temperature is related to the average kinetic energy. So you wanted to construct an algorithm that was given a distribution of the velocity such that it was giving exactly that temperature. So that was my original idea. But then this, of course, works for any temperature. There is not such thing as an optimal values of the temperature. You know, works everything. Otherwise, it's not a good. So when you're at a certain point, your beta was a sort of a temperature. So you know, when you show that there was an optimal value of beta, I got confused. So it's, you know, because in one case it's an inverse problem in which you start with a temperature, you get you wanted to derive the algorithm. In the other case, it's the opposite one. So it's direct problem in which we have the argument, and then you have to find the optimal temperature. So you know.
Yeah. It's probably I probably made the point not sufficiently clear. So the temperature in thermodynamics is a Lagrange parameter to control the expected energy. And so for physicists, what I'm doing is very close to a microcanonical model. Now, in computation, the uncertainty is in the input. But the algorithm, the ideal algorithm, would completely ignore the fluctuations in the input and just treat whatever is the same between original and control experiment as signal. And then you want to convert this signal into hypotheses. So the temperature is essentially a localization parameter, a measure contraction parameter for the posterior, such that the posteriors on two experiments, on two data sets, still agree. And they agree for an intermediate range, as I made it clear with the Gaussians, very broad, but due to normalization, very small values in the product, so you don't get any. Very peaky posteriors, but not agreeing because the data are different. Then they go through the roofs, but the intersection, the product is still small because they don't agree. And somewhere in between, you have this trade-off between width of the posterior and informativeness because of a contracted posterior. And that is exactly what I sell as the optimized version. So I would like to have a theory which operates directly on sets of parametrized posteriors to adapt all parameters which you might have in the posterior such that you control its width. And if you start out with a cost function and you then buy into the concept of Gibbs distribution, that's one family of possible posteriors you can choose. And then the control parameter for the width is very clear, that beta value, which has the interpretation of a temperature. But it's here the effective fluctuations which are in the algorithm to give you uncertainty about the outcome. So it's an effective temperature sort of by converting fluctuations in the input to uncertainty in the output.
More questions on the phone as well? No, I think that was okay. Maybe we can have a look at the chat, but I think yeah, okay, there's one question. Okay, it was not a question. Just thank you for giving this talk.
If I'm not wrong to say at the beginning that see machine learning models as an algorithm that are data driven. So they forward some input in order to add some. I would like to see you, I would like to investigate such algorithms that we have in our mind, like we can write algorithms say numbers, right? It's a set of instructions that I can write down, and for which I have a clear idea of what I'm writing down. And of course, I can debug each instruction that I write down in order to guarantee one of the properties that you write in the process. Now it's like availability, so machine learning models, unfortunately, I see that not possess such properties because the instructions that they have are just trained. So we don't write down the specific instruction that the model has to operate on the diversification or any kind of other condition. But these are some instructions that are self-learned, and for you to do this approximation, let me say, that we don't have the properties that you specify, or some properties. So I'd like to see from your point, do you believe that we can think that as algorithm as it is, or just a subset of something which is close to an algorithm, but for right now they are not algorithm because they do not satisfy properties that we want to have for any algorithm.
So if you refer to the usual case of supervised learning. In supervised learning, the humans tell you what is correct and what is not correct. And you might actually take even errors of the teacher. But in essence, you have a reference. In unsupervised learning, you just know I want to project this data into the hypothesis class with an algorithm. And so that's a more challenging validation. But even in supervised learning, you know that you can have in classification, you can have exponential loss, you can have 0-1 loss, and so on. There are still choices which are to some degree arbitrary. You know, people prefer exponential loss because then they can actually calculate gradients. You know, what the heck? There are algorithms who can optimize without gradients. So you have a lot of different choices. And for me, the situation in supervised learning is similar to unsupervised learning, except in unsupervised learning, it's much harder to tease the knowledge out of users in order to train the machines. So users could easily, let's say, classify shapes by actually drawing boundaries of what they think is the object for which you want to describe the shape. To formulate that as a functional dependence is very complicated. So these types of annotations might help us to make progress on unsupervised learning. But in the end, you have to be able to validate an algorithm out of more general principles. And one principle is, it should be stable under repetition of an experiment. And the other principle is, it should be as informative as possible, but informative with respect to what? It can only be the hypothesis class. So if you have an interesting question is, as we discussed the other day over lunch, you get these gene expression data from your biologist friend. And one of the colleagues in the experiment says, do a dimension reduction. And the other one says, do a clustering. In principle, I think this is decidable, this question, what is appropriate, because if you would know that the data live on a low dimensional manifold, even if it's curved in a very high dimensional space, you want to do dimension reduction. If it's actually very scattered in a high dimensional space, but it's like stars at the night sky with sort of very tiny groups of expressions in all different kinds of direction, you want to do clustering. So you need a principle which actually allows you to trade off the informativeness, because the informativeness of the hypothesis classes might be completely different. So you have to measure the complexity of a hypothesis class relative to the quest of repeatability. And that is a theory which allows it to do that. And I don't know any other theory except of information theory, which is inspiring this type of work, which would help you to do that. And coming back to the theory of machine learning, we were always talking about hypothesis classes with finite either VC dimension or fat shattering dimension or whatever you take. And that was the belief that ultimately, if I do an infinitely large data collection, I get a unique answer out of my inference problem. That is not what reality is. In reality, you get actually maybe a couple of biopsies from your patient, and then you have to make the inference. So maybe you improve your camera and the resolution of your images get better. But that doesn't help you because these are not independent. And the same is true what people do in statistical physics. You are not asking your experimentalists to give you these microcubules of this very precious new material, and then you ask for a zillion of other of these cubes to get your statistics right. No, you have to work with 3, 4, 5. That's it. And this theory addresses it.
I have to say, I have many questions, but maybe I will just focus on a couple and then we will have the other ones maybe for a good glass of wine. So in theoretical computer science, as you know, there are two main concepts when it comes to algorithms, I mean standard algorithms. One is the correctness of the algorithm, whether it performs the right task. And the other one is to do with the complexity of the algorithm. And this notion of complexity also gives rise to a much more complex notion, which is the complexity of a problem. And so we have theory of NP completeness, intractability, and stuff like that. So in this work, we are focusing mainly on the correctness in some sense, right? You're not focusing on the complexity, whatever it means. So the first question is, do you think that in the context of machine learning in general, and more particularly within your framework, the classical notion of complexity of a problem, which is, by the way, from my perspective, it's not satisfying because it focuses on worst case analysis, right? And we know that in machine learning, this is not a good idea. So first question is, do you think that that notion of complexity applies to machine learning in general and to your framework? And if not, do you think there is room for a new theory of a complexity of machine learning algorithms? That's the first question.
I think it applies, but it's not useful if you apply. So, and to be clear, that's not my claim. If you look what statisticians are doing when they write down an estimator, and an algorithm is essentially a super complex estimator in this context, they actually give you an estimator for certain parameter values. And very rarely you have an admissible estimator which holds no matter what the parameter value actually is. And as you know, even for the simple question of estimating the mean of a Gaussian in more than 2 dimensions, with Stein estimation, we don't know what the best estimate is. It's not known. There is no admissible estimate. So statisticians for a very long time got used to the fact that if your value you want to estimate is in that parameter range, you have one estimator. If it's here, you choose another estimator, and so on. Worst case analysis completely ignores that. So I believe in computer science, at least for data science applications, we should think of the scientific object, a data source, and an algorithm taken together. And that's why the algorithm gives rise to a posterior, and the posterior is the model. You condition on the data source, and that is then the model. And so from that point of view, I think we need a new view at what is the scientific quest for algorithms, because algorithms, ignoring the input, allow you to make only very general assumptions. And most of these assumptions are actually not satisfying in reality. You know, the simplex algorithm has no guarantees except of exponential runtime, but it's used every day. So we better come to grips with that.
Well, in this respect, you know, there is this other notion in complexity, which is average complexity, which for some time was also quite popular in theoretical computer science. But as you know, it's very difficult to use because you have to know the probability distribution underlying your problem. So in principle, probably it would be the right answer to this question, but well, in practice, it's very difficult to use.
Well, in some sense, what I'm advocating is that you use such a score for posteriors, because the posteriors reflect what the family of algorithms you have in mind, with all these parameters to be adapted, actually give you as effective action. But then you are not requiring that you know the probability distribution over your inputs, but you have a number of, let's say, samples for input. And then you ask questions for which you can give actually precise answers, or answers according to the precision which you require. And so usually that's why I'm a strict believer in the discriminative approach to machine learning. And that's why I make this populistic statement that I never met a patient who was interested in a reconstruction of their biopsies, but they want to have a cure. The reconstruction of the biopsy might be a complete overkill. So you should be able to have a number of biopsies, samples, and then you select your algorithm according to how they manage a stable compression of information relative to a hypothesis class. And this will work whenever the cardinality of the hypothesis class or the complexity of the hypothesis class is much lower dimensional than the complexity of your problem state.
Okay, I do have another hopefully quick question. So in your framework, basically you abstract the notion of an algorithm in terms of the posterior distribution. So probably I don't think it's wrong to say that this is an information theoretic point of view, and you can say that an algorithm is nothing but a channel. And so first question is, in this respect, do you think that fundamental results from information theory, for example, I have in mind Shannon's channel coding theorem, might be helpful somehow? And also, you know, in information theory, there is this theorem which is called the information processing inequality, which basically says that if you take a number of channels and you create a sequence of all these channels, then you are decreasing the amount of information which travels. Do you think that this result contradicts the notion that nowadays is so popular about having deep learning algorithms?
No, first of all, the information processing inequality is very useful in a context when you just treat information from a syntactical point of view. Yeah. But here we have a semantic notion of information, because information for me is what actually makes a difference in the output space, in the hypothesis class. So these pipelines compress information, not to separate the signal from the noise. The much more difficult question is to separate the signal which helps you to make a decision from the signal which has nothing to do with your decision making. It has to do with other questions you might want to answer based on the same experiment. And so you have to develop a context-sensitive notion of information, and the context is set in this theory by the assumption of a hypothesis class. So I compress the input information I try to compress the input information in the best possible way that it gives me the maximal amount of bits out of this pipeline to localize in the output space. So in some sense, the task is to preserve all bits which tell you something about the survival probability of a patient, and to separate them from all the other signal bits which deals with the staining of your tissue, any kind of knowledge about where the tissue exactly in the liver, in the kidney has been extracted and so on. Science is about separating relevant signal from irrelevant signal. And then there is the nuisance of the noise. But that is not the very big question. The big question is what helps you to solve it. And for this, you need a context-sensitive notion.
Okay, so there's no other question. I would like to. The question. Oh, there's a question. What? So the question for me, not for you. Okay, it's fine.
So, my question was looking for that you have some and what you want to find is that why not apply
because no human can actually control the complexity in these interpretations, nor do we have a concept for doing it. So in some sense, what you are suggesting is exactly what I tried to do. So you have a family of posteriors, and so what we do we also applied it to sorting under uncertain decisions. So imagine that you have a sorting algorithm. You ask an oracle for whether A is larger than B, and occasionally that oracle tells you that 5 is smaller than 3. So if that happens too often, you can't do anything to sort. But it happens only occasionally. You find algorithms which completely break, and others which are robust with respect to these mistakes, because they don't care if in 10% the decision about the total order is wrong. And so resilience of algorithms is something which you can explore systematically, and then you actually have to make a trade-off between efficiency in computation and resilience to let's say, wrong decision making. That is something you can quantitatively capture. And that's exactly what the theory tries to.
why?
You can because the benefit in supervised learning is too small in many cases. On the other hand, right now, nobody knows why deep learning is working. And let's be honest, in deep learning, people tell you we are optimizing something. Then when you actually look, what they do is they are not optimizing, they are stochastically approximating, sucking on their fingers when they should stop the noise decay. And then they also pitch in with dropout, all kinds of perturbation to the solution space. And all these are tricks to increase the entropy while still maintaining a certain level of quality. I think they are doing poor man's statistical physics in a computational setting. And then you have to actually see that the best predictions, when you use these concepts, apply that to the deep learning scenario, that this is actually what works. So that's my guess. Why am I not doing it? Because I don't have enough time.
Okay, so I would like to thank everybody for
I'm going back on Thursday morning, so I'm here until Wednesday.
So we will be given another Friday. Thank you.